My name is Temitope Damilotun Soneye, and I am a graduate researcher at North Carolina Agricultural and Technical State University. My work is on the optimization of hydrothermal liquefaction reactions for the destruction of organic contaminants using nanoscale catalysts. In plain English, I'm trying to find better ways to clean drinking water. I became passionate about water treatment after having some internships in petroleum producing companies. The amount of petroleum waste being generated and how much of it is being transmitted to the natural environment is just predominantly water bodies is alarming, more than 300 million gallons annually. This made research into contaminant destruction technologies interesting to me, and I seek to make valuable contributions in this space. Water reuse involves gathering water from multiple sources and subsequently treating prior to industrial applications, irrigation, or use as drinking water. Currently, 1 in 3 people globally do not have access to safe drinking water. The stress for water is expected to increase in the coming years with a forecasted population of 9 billion people in 2050. Contaminants are impurities present in toxic quantities in water bodies, thereby rendering them unsafe. PFAS, a classical example of these contaminants, are groups of everyday chemicals that are being phased off due to toxicity concerns. In the United States, for example, almost 200 million people have tap water contaminated with 1 part per trillion concentration of PFAS. These chemicals have strong carbon-to-fluorine bonds, meaning they can accumulate adversely in water without breaking down. Exposure to PFAS-contaminated water has already been linked to cancer, liver damage, and genetic mutation. Conventional treatment methods have not been overly effective in removing these contaminants. Mainstream water treatment processes, such as biological and physicochemical treatment methods, have been found to suit just a particular class of contaminants per time, while membrane separation processes create residual PFAS and reject concentrates. There is therefore need for a more holistic approach to treat contaminated water in order to achieve Sustainable Development Goals 6 and 13. Hydrothermal liquefaction, HTL, is a technology that uses heat to break down biological molecules into smaller ones in the presence of water. It is termed a carbon negative process because it does not contribute to the carbon dioxide emissions, thus making it a green way to produce energy and mineral resources. Studies have shown that alkaline amendments are capable of destroying the PFAS structure, but these are expensive. The next stage of investigation, therefore, is to assess how nanoscale catalysts can help promote further degradation. In other words, by making the catalyst smaller, we can clean more water using less energy. In summary, it is important to stress 3 fundamental considerations. Firstly, there is an urgent need to rid our water bodies of contaminants if we are to ensure clean and safe water for a teeming population. Secondly, it is clear that conventional water treatment methods cannot meet the requirements of both present and future water needs. Lastly, water treatment fiscal regimes need to be tweaked to accommodate nanomaterial catalyzed hydrothermal treatment processes. Consequently, clean water can be realized in a sustainable manner. Thank you.